electrostatics is using a balloon and simply rubbing it across your head, and very quickly it becomes charged. In fact, if I lift it off my head, I can feel my hairs being attracted, and so they're attracted. But if I take the same balloon and I put it on the wall, well, let's see what happens. It stays there, but I haven't done anything to the wall. So the question is, why is it... Now, if I take this glass and I rub it with Coulomb, I'm going to give it a charge, and watch what happens when I bring it near these small pieces of foam. Now, what makes it an insulator? Well, their electrons in their atoms are bound up and they're not able to... Now, we'll get a nice charge on our PVC pipe here and see if we can move it. Hey, there it goes. See if I can reverse directions. With induction charging, I don't have to touch the pipe to the wood, I just have to bring it near it. Let's try it on a smaller scale. Here's a positive charge brought near some little dots of paper. Let's see that again in slow motion. The equipment is the electroscope. These devices were originally designed to detect and measure static charges. This one has two pieces of aluminum foil hanging down from wires attached to a bolt, comes up through the center, and has a large metal ball sitting on top of it. Let's try it with a negative charge. Now in the previous video we looked at the behavior of charges. In this case these vinyl strips are negatively charged, so they repel each other. When these acetate strips are rubbed with Coulomb, they become positively charged, and as we can see
Electric forces compete well with gravity. Turn on my charging arrangement, please. Give a charge to the balloon. Collect a like charge on my balloon. They repel. At closer approach, more. Bigger force. You probably know already. Coulomb's law says force varies inversely as the square of the distance between the charges. Here it is. Fiber, twisting beam, two balls to carry the charges. In our experiment, we shall use a spring balance to measure the force, like that. Two metal balls that we can charge up, a beam carrying one, and a spring to balance the force between the balls. And over here, a pointer which will show the stretch of the spring on this scale, and that gives us an estimate of the force. I'm going to ask my assistant to take the upper ball away, and we can see if the zero is correct. I should like you to see how sensitive this is. I have here a box of weights. 1 gram, that's too big. 1/10 of a gram. I'm going to ask you to put on 1/10 of a gram on the ball, please, and we'll see what that does to the scale. Now first, let's settle the zero. First, just wait while I settle the zero. I'm tapping the balance to free the bearings. Starts with a zero. There, about there. Now put on 1/10 of the gram. Load it up. 1/10 of a gram is within 2%, 1,000th of a Newton. And you see it's going to settle down very close here to 10. And so each of these scale divisions represents 1/10,000th, roughly, of a Newton force. Take the load off, please. Now I shall show you how we measure the distance apart of the two balls. We move them till they're 1 span apart, or 2 spans apart, like that. I'm going to call each of these distances a span, though in fact you'll see that they are pretty well 15 centimeters each. 15, 30, 45, but we shall not use those numbers in our experiment. I shall just call them 1 span, 2 spans, 3 spans. Here is a record. We shall have distance apart and force, and we shall run from 1 span to 2 to 3. We shall start with one ball far away at infinity, and like this. And then at infinity the force is going to be 0 because we'll start the pointer there. Then we shall start 1 span. First I must charge up both balls. I'm not going to explain this ancient device for charging, except just to say that it operates by induced charges on the plate that I'm carrying. I think that will be perhaps a little more sufficiently charged. Now, please set the balls 1 span apart while I look at the scale. There we are. Force is at 1 span, please record it, between 23 and 25. It's just about 20. Settle down, it'll be 23.7. Now 2 spans, please. Oh, force is much less. Well, what did you expect with an inverse square law? Still further up. Okay. Encourage the pointer to stop moving. between 4.8 and 4.0, about 4.4, please. 5.4. Sorry. Thank you. Now move to 3 spans. Still smaller force. 3, 2, 2.903, about 2.5. 2.5. Now let's see what that record tells us. When I go from 1 to 2 to 3, an inverse square law makes the forces go down from so much to a quarter to a ninth. And we can test for that by multiplying them by 1 and 4 and 9 to see if we get constant numbers. 23.7, we'll call 23.7, 24 would be near enough. 4 fours are 16, 4 fives are 20, 21.6, say 22. And 9 fives are 45, 9 twos are 18, and 22.5, 22.5. So that I get very closely the same number